Hello, everyone. We found Kourou again, so we are back to, sorry for the delay. We had some problems of communication, but I guess everything is solved, and all our guests are squeezed, as you will see, in a tiny screen to answer your questions. So before we go to Kourou, okay, let me first welcome all the learners from Gravity, but everyone else who has been invited to join this very special hangout. And so on our side, so I'm Pierre Binetruy, and this is Volker Beckmann. Most of you know him because he has been answering many of the questions on the Gravity course. So maybe Volker, before we go to Kourou, maybe you should say a few words about where we are.
Yeah, we are at the François Argot Center. That's a data analysis and computing center here at the APC in Paris. And one of the missions we are involved in is LISAPathfinder. So you see behind us our operations room. So during the active mission of LISAPathfinder, we will work here on analyzing the data of LISAPathfinder, trying to help the team to make this mission a success.
Okay, so let's go to Kourou, and so let's join Paul. Paul, can you hear me?
Yes, welcome, Kourou.
Okay.
Hi, can you hear us?
Yes, we can hear you fine.
A little bit closer to the.
So can you show you that you're in Kourou and not in an office? I want to see some jungle.
Maybe over there somewhere you can see some jungle.
Okay, good. Okay, so now we trust you.
Unfortunately, there's no Wi-Fi in a jungle, so we have to do it from an office.
Okay, very good. So maybe I'll ask question to each of you so that all our listeners get to meet you. So let us first start with you, Paul. You are the project scientist of LISAPathfinder. So could you describe in a few words, what is your role?
Hi, so my name is Paul McNamara, and as Pierre said, I'm the project scientist. So my job is to coordinate the science of the mission. So one side of it means working with the engineers so that the hardware is meeting the science requirements, and the other side is coordinating with the universities to ensure that we have the right data analysis tools available to us to analyze the data. Yep.
And maybe one first question to you. Could you, most of our learners, have been going through, a week on gravitational waves and even a short introduction on LISAPathfinder. But could you remind us of exactly what is the principle of the mission? We'll get back to the details. We have many questions, but could you let us know in a few words, what is LISAPathfinder about?
So LISAPathfinder is the first step towards a large spaceborne gravitational wave detector. It's to make a gravitational wave measurement, as you've probably heard, is a very complex process. You have to measure extremely small distances over very large arm lengths, large detectors. And there's always a worry that that's not possible. So LISAPathfinder was instigated by the European Space Agency basically to test the technology principle behind a large gravitational wave detector in space. So what we're doing is we're effectively testing the parts of the technology which you can test on Earth due to the Earth's gravity, which would interfere with the measurement. So we have to go into space to allow us to do this demonstration.
Okay, thank you. So maybe let's move to Caesar. Caesar is the project manager of LISAPathfinder. We'll be speaking in turn, so don't worry. So Caesar, could you tell us a bit more? What is your role?
Hi, again, my name is Cesar Garcia, and I work at ESA. I'm the LISAPathfinder project manager. And my role is to make sure that everything happens, from the technical work done by industry, and then also the integration of the instruments done by the scientists in various places, to prepare the operations from ESOC to ensure that the launcher system is ready for us, to make sure that everything happens with some planning and that it all fits within the budget. So this is what I do.
And since you're a project manager, we'll come back to that, but could you tell us in a few words, how long was this project and, how long it took? And we'll come back to the details, of the project, because we have quite a few questions, especially on the mission payload. But, how long did it take to, from start to the launch?
Okay. That's an interesting question, because to me, the mission started maybe about 25 years ago when people started to think about an interferometer in orbit to detect gravitational waves. More specifically, towards the end of '99, there was an idea in the UK to propose a mission that could be doing technology for space detection of gravitational waves. Then in 2004, the governing body of science in ESA, the Science Program Committee, adopted the mission, which means that they gave the go-ahead for detailed design, procurements, and launch and operations. That was in 2004, towards the end. So we've been developing this mission for many years, and it took us a bit longer than we thought originally, because we are a technology demonstration mission, and that means that sometimes we have to change things as we go. There were some of the technologies we have proven already with LISAPathfinder were far from being proven when we started, so it took a bit longer than we thought. But I would like to finish my answer to your question in saying that it took us a bit longer to finish, but it places us a huge leap ahead. Once we fly this mission and once we prove the technology, we are really many years ahead with respect to our partners all over the world in taking this first step to gravitational wave detection from space.
Okay, thank you very much. So now we turn to Vicky Lonan from Airbus Defence and Space, with quality assurance engineer. So maybe you should tell everyone what is a quality assurance engineer, because I'm not sure everybody knows about this.
Hi, yeah, so my name's Vicky, nice to meet you all, and as you said, I work for Airbus Defence and Space in the UK, and yeah, I'm the quality assurance engineer for the assembly, integration and test part of the mission. So basically I've been with the spacecraft while we've been building it, and what do? Well, I act as the conscience for pretty much our manufacturing team and our test team. So any time that they want to do some work, they have to pass the paperwork by me. We make sure that everything we're going to be doing is going to be safe for both the people and for the spacecraft, and we also have to make sure that we're going to meet all the requirements that CESA's placed on us and Paul. So we're trying to make sure we deliver exactly what we've been asked to deliver where possible.
And so this means that the spacecraft has been built by Airbus. Is that right? Because sometimes people don't know whether what is built in the laboratories, what is built in the industry. So that means the satellite has been built by Airbus.
Yeah, that's right. So basically, Airbus in the UK, we were Astrium at the time, as the prime contractor for the spacecraft. So we have actually built the entire spacecraft, both the propulsion module and the spacecraft. I'm assuming your listeners know and the viewers know that we've obviously got the two parts. We've got the propulsion module and the spacecraft module. And we've also then brought together all the various different instruments from industry. So we've had the actual LISA technology package, the main beating heart of the instrument from Airbus in Germany, who are our sister company in Germany. They've delivered that, and obviously lots of different instruments through them from various places like Imperial College. I'm not sure of the entire list of all of them. I couldn't remember.
We will go through.
But there's a long list. And then obviously we've also bought and put together all the different parts that you need just for the platform to actually keep the spacecraft in space. So things like the onboard computer, making sure that we've got a solar array to keep us powered, the avionics systems, everything like that, all the propulsion, that's all been put together and built by our team. And actually quite a few of them are out here now with us at the launch site, where we've done some last bits and pieces. And
don't forget the testing. The testing.
Oh, and also on the test campaign for the last. We did a test campaign this year for 6 months, and many of them also did the test campaign back in 2011. There was another one, so it's been a long haul for a lot of people at Airbus as well.
Okay, thank you. And our fourth guest is from the Kourou Space Centre. Jean R. And so you're, as I understand, the Directeur des Opérations, DDO in French. So can you tell us, what this is all about?
Yes. So hello everybody. So I'm John Har from CNES, and I'm, as you say, the DDO for the BB06 launch. The DDO, or Range Operations Director. His role is he's most well known for the final countdown. So we manage the countdown operations from the Jupiter 2 control room. But of course, this is not the only thing a DDO does. A DDO, he follows the launch campaign from the very moment that the spacecraft arrives at the range, and manages the spacecraft preparation campaign all through the preparation phase, and until the time when the spacecraft goes until on the top of the launcher. And in parallel with that, we prepare the range for the launch. So the range is like an airport. It receives not aircrafts, but the launchers. And the role of the DDO is to prepare all the means on the range to be able to track the launcher once it lifts off. And we do that from very many months before the flight until the liftoff of the launcher, and until the end of what we call the positive chronology, which is until the spacecraft is put into orbit and we have finalized our tracking mission.
Okay, so we understand that you're a very central person for all the events that are taking place and will take place. So I understand that you were all at readiness review. So maybe you can tell us the latest about the mission. Jean. Oops, I switched my microphone too early. So is everything going well at this point?
Yes, so we just, as you say, we just came out of the launch readiness review, and the conclusion of the review is positive. So we are going for launch tomorrow. Of course, tomorrow we start the countdown, but we launch on the 2nd, on Wednesday morning at 1:15 local time here.
Okay, I have slight problems with muting my microphone. And so, because this is a French center, the countdown is in French. Is that right? So that nobody be surprised when they hear the countdown on Wednesday morning for us.
That is correct. Yes, all operations, launch operations, are conducted in French here at the Kourou Space Centre.
Okay, so let's move on to questions. So we have prepared a set of questions that we received over the last days, but there are also questions coming in. I would say pouring down, on the Q&A also live. So we'll try to pick some of them for some of the old ones and some of the new ones. So Volker will help me. So let us try. So that different types of questions. So let us start with what I call the payload questions. So the questions about the instruments and all that. So we had quite a few questions about test masses. So for example, Jim asked us, are the test masses material was chosen? He says that that they are made of gold and platinum. So, you know, why is that? And maybe we take another question on test masses by Michael. You know, how large are the test masses, and are they maintained in the center of their boxes? So who wants to answer this question?
But I'll take that one. So first of all, we can do the size. The test masses are 46 millimeter cubes of gold platinum. So why do we choose gold platinum? There's actually two reasons for that. The first one is that we want to have as dense a material as possible. And gold platinum is a very dense material, something like 20,000 kilograms per meter cubed. So for our little cubes of 46 millimeters of the gold platinum, it weighs about 2 kilograms. And why do we want it to be massive? Well, if we think of Newton's laws, we have force equals mass times acceleration. For any given force on the test mass, divide that by the mass, that gives you the acceleration. So the higher the mass, the less acceleration you get for a given force. So we want to have something which has a very high mass, but it doesn't take a high volume because we have to fit it inside the spacecraft. So that was the reason for choosing the dense gold platinum material. The other reason why we want gold platinum rather than something like tungsten or some other dense uranium, for example, is that we want to make something which has zero effect to magnetic fields. Gold and platinum have opposite signs of a parameter called magnetic susceptibility. So depending if you put a magnet near it, how does it react? So if you take a positive material and a negative and you combine them at the right ratio, in our case it's 73% gold and 27% platinum, and you form the correct alloy, then you can effectively wipe out its magnetic signature. And we do that, and we have a very, very low magnetic susceptibility. So it's a combination of magnetic susceptibility and density is why we chose gold platinum. I think the other part of the question was, how do we maintain the cube in the center of its housing? So there we basically have the test mass itself, the gold platinum cube, acts like one face of a capacitor. And then we have a housing that goes around the cube, which acts as the other face of a capacitor. And we can actually do an electrostatic actuation. So we can use the cube itself as one plate of a capacitor, and then we can drive electrostatic forces to keep the test mass located where we want it to be. But in reality, when we're operating the spacecraft in science mode, the test mass is completely free, and then the spacecraft flies about the test mass. So we monitor its position, and then we force the spacecraft to follow the test mass's position, such that the spacecraft becomes a shield of the test mass.
Okay.
Answer the question?
Yeah, absolutely. Yes. Another question, which is on the principle of a measurement, that from Brian. When you're going to be measuring such a small amounts of displacement, how will you be able to know with sufficient certainty that the displacement is due to gravitational waves and not to the numerous other forces that could cause such a displacement? Who wants to answer this one?
Okay, I'll take that one again. So LISAPathfinder itself is not a gravitational wave detector. It's really just testing the technology. But if we think of the LISA detector, so LISA is a detector where we have 3 satellites, and the satellites are separated by 5 million kilometers. So 5 million kilometers is about 13 times the distance between the Earth and the Moon. So it is a long way. And we have to measure that distance to about 100, maybe a tenth the size of an atom. So it's quite an enormous variation between what we have to measure over the distance we're measuring. It's something on the order of 21 orders of magnitude between the two. So the question is, how do we know that we're measuring a gravitational wave and not something else? One thing which we can do with LISA, by having the 3 arms of the LISA triangle, is we can actually cancel out the gravitational wave measurement. So we can actually combine all the signals such a way that we take the gravitational wave measurement and we deliberately delete it from all of our data. And that gives us a measurement of the noise of the detector. So we can actually build up a certain way of combining all the results such that we can measure the noise of the detector. So we immediately know how much force is acting on the test masses and the spacecraft. We can then combine the signals in a slightly different way where we keep the noise, as we keep the gravitational wave signal, and we delete some of the noise of the detector. So in that way, we have a very clear measurement whether we're measuring gravitational waves or we're measuring noise kicking the test masses.
Okay, thanks. So I think we have one question here for the project manager, Caesar. This is a question from Dana, who is asking, this project has been in development for many years. Did you encounter problems with obsolescence or a need for entire redesigning? I think you'll appreciate that question.
Yes, thank you for the question. The answer is yes on both accounts. Okay. With respect to obsolescence, there are life-limited items on every spacecraft, and then the fact that the mission took longer meant that we had to procure new of these items. That's one element of obsolescence. Then the second part of that question is that the technology in many areas has changed. And sometimes, and it happened to us on one of our ground equipment, which is basically a rack full of computers, the motherboard died. Now, if that computer would be a new computer, it would be easy, and then you buy a motherboard which is out in the market. In our case, that computer was already a few years old, and the motherboard for that specific computer, and you don't want to change that because then all the interfaces, they change a little and a bit and so on. We had to go into Google or some places on the internet, and we found one in Germany, which had to be bought locally and then transported to the UK to be able to replace the board one by one. So that's, yes, the answer to the first question of obsolescence. With respect to the change of design, I think this is one of the key reasons why the mission took longer than planned. When you're trying to develop new technology, sometimes you go into roads which have no end, and you have to go back, you have to redesign, and it's difficult that once you are midway in the detailed design phase and in the procurement of all the other spectrum and payload elements, that the new proposed design fits well, because there are many interactions at system level. So there are interactions at unit level, so how every unit talks to the central computer. That's one, how the bolts are, how do you fix this, the box to the spacecraft. These things are relatively easy, but there are many interactions at system level. And all these interactions need to be covered by any change of design. We have changed the design, we have changed the implementation of LISAPathfinder in a number of areas. We have changed the propulsion system of the science craft. Our propulsion system is very delicate. It provides only a few micronewton. That's millionths of a newton. And again, we should compare our classical number of 3 to 30 micronewton to the force given by the Vega launcher vehicle, which is 3 meganewton, is 12 orders of magnitude. We have to change the design and the implementation of those. We have to change as well things like the test mass that Paul was describing earlier. We did the first attempt at manufacturing the test mass, and we realized that the manufacturing process was not perfect enough to ensure homogeneity inside, because it's solid, gold platinum. So we had to change. We had to change the manufacturing process of the alloy itself, and we had to change the design of the features to hold the very heavy test mass safe during ground operations and launch. We changed the way in which we protect this test mass from some of the interactions, like for instance the interactions with free-moving particles around the test mass itself, what we call the vacuum within the vacuum of space. We also changed a little bit the approach to the design and the verification of the software. We have changed a few of the things which are now I don't come even to mind. And all of these changes, we changed also the design of the electrode housing, these electrodes around the test mass. We had technological problems. It's not that we had conceptual problems, it's that we had technological problems. You expect certain technology to do a function, you design everything around it, you do sample tests, but once you put everything together, once you put the system together, or in this case the subsystem together, you hit a wall. And then you try hard to fix that problem, and until eventually you realize you have to change the design. All these things imply pain, sweat, and time. And this is this is why it takes longer, and I think this is the answer to the second question, I hope.
Yes, thank you very much. So we have another question which is fairly appropriate to the situation we encountered earlier, which has to do with redundancies. So what redundancies are built into the system to compensate for component failure? This is a question from Kathy. Who wants to take that one?
Well, I looked around and they're looking at me. Redundancy. Okay, I forgot one change to our mission. When we started the mission, we were not supposed to go redundant. And then soon afterwards, in agreement with Airbus, we realized that it was not worth going to space with such an important mandate overall, I mean, enabling LISA in the future without redundancy. And that meant that we had to change the concept from non-redundant into redundant. What are the functions that we have redundant? We have most of the spacecraft functions are redundant. We have an overall requirement of redundancy, and that means that when a specific function cannot be made redundant, we have to implement design or verification features to be sure that this thing will work. And I'll give you an example. This structure of the spacecraft is not redundant because you cannot have things bolted on two different plates. So the structure of the spacecraft is not redundant. However, in our design requirements and criteria, we need to ensure that there are sufficient margins. So we build in additional margins with respect to loads that could break or misalign the structure, so that we have the certainty that the flight loads are covered, that then the qualifications, so with the margin loads are covered, and a bit more. So this is one. Now, what do we have redundant? I think most of the functions are redundant. There are some switches which are difficult to make redundant. So when you have to switch between a unit and a different unit performing the same function. That switch is extremely difficult to make redundant. So you have to be damn sure that that switch will work. Again, we go into margins. If it's a mechanical switch or electromechanical switch, then what we build is mechanical margins, and also we do a lifetime test. So we exercise identical units for many more operations that will be necessary during flight. And then we gain confidence that the lack of redundancy of the component itself is compensated by a longer life than really required in orbit. I don't know if anybody wants to say something. I don't know if they. We don't know. We don't hear if they, or we don't know if the people listening are satisfied with the answers. Okay,
they will let us know on in whichever way, by Q&A or by on the platform. Someone is checking the platform, so we'll tell you if they're not satisfied. I think I think they are. But so maybe a question to Vicky about integration and test. Maybe you should explain to us what is integration and test. And maybe answer in the end a specific question from Steve, who is worried that when you put to vibration test components of a satellite, they might be fatigued and then break up during launch or after launch. So could you tell us a little what is integration and test?
Sure, no problem. So we'll go straight for answering the question. Essentially, when you build a spacecraft, we build several models, and especially if it's one that we've never actually built before, so if it's not a generic platform, then we have what we call qualification models. You have a structural test model, which is, to all intents and purposes, from a structural point of view, exactly the same as what your flight model will be, the one you will actually launch. And we put that through really rigorous testing. So we put that through what we call qualification level testing. And that is usually levels which are ever so slightly above what is really going to see. Like Cesar was saying, we put the margins on the top, and then we test above the levels that we're really going to see. And then we analyze the data we get back from that, and potentially maybe work in some redesigns if we've had any problems at that point. And that's done, as I said, with this structural model. Then we move on from there and we can start building our, what we normally have is a proto-flight model. So we've had a proto-flight model that more often than not turns into what will be the flight model. And we do actually do a series of tests on that. So we vibration tested the flight model as well in 2011. However, that one, the vibration test, is done at what we call acceptance levels, which are lower than the qualification levels. So they're more akin to what we really expect to see the real spacecraft go through. And obviously, while we're going through all of those testing, we're checking everything at the time to make sure that we don't introduce any fatigue. Beyond that, probably the hardest, or one of the hardest tests that the spacecraft has to go through, and its very, very final test before we actually shipped it to the launch site, was the acoustic testing, and that is simulating the environment within the fairing of the launch vehicle. So it's basically a huge noise chamber, and we blast lots of noise at the spacecraft, and we check that it's going to survive the launch environment. And of course, as with anything, you shouldn't fatigue it before you fly it, but we have to test the real one because you just don't know what material differences you could get if you went away and then built another one that you never tested and put into space. So we do have to basically fly what we test, and that's what we always try to do, is fly what we've actually tested. We do the same with a thermal environment. We check out the spacecraft for a thermal environment and how well it's going to respond. And of course, we will actually easily detect if anything has gone wrong, because after each test, before and after each test, we do a series of checks. So we do things from the obvious, like visual inspection, which is one of the key jobs that I perform. So I go around, make sure, so for example with acoustic testing, that you don't find bolts on the floor. That's seriously worrying if you find bolts on the floor. And we check that nothing's moved. We do alignment checks. We make sure before and after, and we basically compare the two, and we report any differences. And certainly we don't get that many differences, and there's obviously a tolerance level to which you expect to see small differences in things like a tiny amount in alignment. And then we also do electrical checks, so we'll completely functionally check out prior to a test and afterwards how the spacecraft is actually working. So we do that with our electrical team, and they will actually power the spacecraft and run it through a series of checks, make sure all units are still communicating. And if we find any problems, then we raise a beautiful thing called an NCR, which is a non-conformance report, and that's where really the quality job really comes into play. It's our job to then drive that through to completion, to get all the right technical people around the table, make sure we get to basically an answer. Either it could be a use as is if it's something that we're not particularly worried about, or if there's nothing you can really do, or we might have to actually rework and rebuild, and we've gone through a series of many minor and in some cases major rework and rebuilds for various issues that have cropped up. And then obviously you have to prove that that rebuild hasn't affected anything. So it's a constant feedback loop going round and round to make sure that on the day tomorrow when we launch that spacecraft, we really truly believe that that spacecraft is ready to go into space.
Okay, thank you very much. I think we get now better picture of what it means to build a spacecraft. Volker, you had
Yes, there's a question by Magdalena which seems to be very popular with the learners, and that's about what do you think now after all this testing and everything? What is still the most risky part of this mission?
Who wants to answer this question?
But okay, make sure. I mean, and next to me here is John sitting. Make sure that I get some questions as well. Now, if it comes to risk, I think I have to. It goes in my payroll answering that question. Okay. Okay, launching a spacecraft, it's always a risk. Always a risk. Tomorrow, well, actually Wednesday morning, we are going to put in space a spacecraft. And the amount of energy stored in a launcher vehicle is so big that they have checked everything, they have double-checked everything, they have triple-checked everything. But I think you can. That's always a big milestone. Okay. Now, the next thing is once we go into orbit, what follows in the next 10 days is new. The orbit raising maneuvers that ESOC will be commanding from Darmstadt, they have never done before in a similar fashion, so that entails a certain risk. But I would assign a medium level to that risk. The next thing is we'll have to study spacecraft systems and so on. It's also low level risk. I think once we go in about 50 days after launch and we separate the propulsion module, and every separation is risky. Okay, but again, this is a mild risk because we have tested this separation in a number of ways. Then we switch on the instrument, and the instrument is new. The instrument being new means that many of the functions, most of the functions, nearly all the functions of the instrument, we could test on ground. And we have tested exhaustively. Vicky was saying, you fly what you test and you test what you fly. This we have done for nearly everything, with one significant exception. And that is the release of the test mass in free-floating conditions within its electrode housing around. And the reason why we have tested this function in many partial ways, in as many partial ways as we could think of, but we were not able, because of physics, to test the full function of releasing the test mass from a held condition into a free-floating condition at very, very low speed with respect to its housing. By very, very slow speed is somewhere between 5 and 10 microns per second. So this function we have tested partially. We have tested property of materials, behavior of the various elements, design revisions, testing in representative conditions, but never in fully representative conditions. So I have to answer, to me, the riskiest moment of the mission, barring the launch, would be this release of the test mass. 2nd of February, according to the plan.
Okay, well, thank you very much. So now let's move to the mission. So we are, as you say, a few hours before launch, less than 2 days now. So, Jean, can you tell us exactly what have been the major steps in the last days and what is still to come before launch, before the final countdown?
Yes, so the major steps during the last week were we had a range test, which was really important last Monday, when we validated all our systems, including all the ground stations. So the ground stations are spread out all around the world. We have in here in South America, we have a ground station on the Ascension Island in the Atlantic, 2 in Africa, and we have a boat which is north of Colombia. So all this has to work together at the same time and communicate perfectly with the range here in Kourou. And this was tested last Monday. Then in parallel to that, the launcher, of course, we have these 2 lines, which are the range and the launcher. They go parallel until the general rehearsal. So before the general rehearsal, we had the launcher preparations and putting the combined, the fairing with the spacecraft inside on top of the launcher was a very important step. It also happened last Monday, and fixing it to the launcher, and then the upper stage of the rocket, called the Avoom, was fueled during 3 days last week, from Wednesday to Friday, with this storable propellant, which will be used, of course, once the rocket is up in space. And then we all met launcher and range and spacecraft team on Saturday, and we had the general rehearsal for the launch. So we played a simulation of the whole launch chronology, and it all went very well. So those are really the important steps in the last week. And now today we are doing the final preparations for the countdown, which will start tomorrow. So it's really the final preparation. The last safety is doing their last training on the launcher side. They are doing the last inspections, removing red tag items, preparing for the gantry removal, because the top of the launch now is a gantry, mobile gantry. It has to be removed the day of the launch. So all these preparations are now ongoing, and tomorrow during the day, I think we will relax a little before we go and take place our seats in the Jupiter control room or the launcher control center, and start the final countdown.
Thank you. And you know, our learners will, you know, some of them, and we will be, you know, watching the launch. So, can you tell us, you know, what are the important events in the first minutes, you know, after, you know, once, you know, you have the liftoff?
Yeah, so the important events after liftoff is, of course, from our perspective, is the safety aspect. If we, CNES, the French space agencies here, our responsibility is to protect people, property, and environment here in Kourou, and so we managed to assure that of course there's no risk for the population. So this is the first 4 or 5 minutes of the launch. It's the critical time for this. So this is a very important that we track the launcher with different radar systems and telemetry stations that we have here locally. This is very important for us. Of course, on the launcher side, we have the separation of the first stage, then separation of the second stage of the fairing. All this happened within only a few minutes after the launch, within visibility of the Kourou ground station. So many events happen very shortly after launch.
And so when you decide that the mission is a success, the launch is a success, at what time? Basically after liftoff?
After liftoff, we will have the launch is a success when the spacecraft is successfully separated onto to its right orbit, and this happens almost 2 hours after the launch.
Okay, well, thank you. So we have one question from Neil. How long will it take after launch to get LISAPathfinder on its correct trajectory? How difficult is this to achieve? And when do you expect it to arrive at L1? And how much fuel will then be required to maintain a halo orbit around L1? So, who wants to answer this one?
I'll take this one. So the question was, if I try to repeat the question again, how long will it take to get to L1, the question? So after we separate, as John said, it's roughly 2 hours after we launch, we separate LISAPathfinder from the launcher. We then remain in an Earth orbit for about 4 days. And after 4 days, we then use our own engine, our own propulsion module, and we start to increase the size of the ellipse of the orbit around the Earth. We call it apogee raising. And we actually fire the engine 5 times to continually make the orbit slightly bigger. So we start off at 1,540 kilometers apogee, and we eventually boost that up to a few tens of thousands kilometers. Then with the 6th burn of our own engine, we then actually leave the Earth completely. So we get a transfer orbit. And that then takes us out towards the first Lagrange point, which is 1.5 million kilometers from Earth. So we take about 12 days before we do this final burn to go to the Lagrange point, and then we get to our final orbit about 8 weeks after launch. So we're talking about 6 weeks of cruise phase to get out towards L1. And then we end up in a LISAPathfinder orbit around the Lagrange point, and that's an orbit of about 800,000 by 500,000 kilometers orbit radius. There was another part of the question, I've forgotten what it was now.
How much fuel?
How much fuel, yeah. So in order to get to the final orbit, we have 1,200 kilograms of fuel within our own propulsion module. So we use, I think, I'm looking at John here, but we have something like 110 to 120 tons of fuel on the launcher, plus our own 1.2 tons once we're actually orbiting the Earth to get us out there. Once we actually get to L1, I think the question was, how do you maintain the orbit around L1? At that point, we only have micronewton thrusters. So as Cesar mentioned earlier, we go from having meganewtons of thrust on the launcher to micronewtons of thrust on the spacecraft. And just to give a little perspective what a micronewton of thrust actually is, if you were to take a standard piece of A4 paper, just a standard sheet of paper, it would take approximately 1,000 thrusters to lift that piece of paper off the table. So it's 1,000 of our individual thrusters to lift the paper. On LISAPathfinder, we have 6. So not 6,000, 6. and our spacecraft weighs 450 kilograms. So we don't have very much fuel. I think in total we have 8 kilograms of fuel on board, but that's enough to maintain the orbit and to perform the science.
Okay, well, thank you. There is a question from Will, and maybe you could give different answers. This question from the Q&A, Google Hangout questions. How many people altogether have worked on this project? So maybe you could tell us, how many people at, average numbers, how many people at ESA, in member states, in the scientific community, but also, how many people are needed, for launch at Kourou, and how many people have been working in the industry, just to give a sort of an idea of the size of such a project.
So I think we'll do it in a particular order, where you have the development phase, the building phase, the launching phase, and the operations phase. So, Cesar?
It's a difficult question. I'm afraid we don't keep the records. That is a problem. We don't keep the records. I would say that during the development phase, there were, at any given time, would be around 300 people working all over Europe. I would say there would be in the States 20, 25 people, including industry, at a certain moment in time, maybe more. But it's really difficult. I regret I don't have a list of every person who has worked on this mission in the last 12 years. But let's say during development, including science institutes producing the items of the instrument, various companies across Europe, I would say something around 300 people, not counting, of course, people here in Kourou, or people related to the launcher vehicle, that maybe you have a better view, Jon, or in the latest phases when it was mostly Astrum, or now you guys will science, but okay, maybe you have something to say.
Yeah, well, from the range at the launcher side, I don't have a very clear vision of how many people's actually worked on it. I mean, the launcher takes months to build, and many, I would say hundreds of people have participated in different phases, building the different stages. They are built in different places around Europe, shipped here. Some are built or at least finalized here on site. Then we have the teams who construct the launcher here in Kourou. So it's hundreds of people, that's for sure. On the range side, I know that just for the chronology, for the last chronology, we have between 200 and 300 people working at different sites just for the launch. So that gives you an idea.
Yes, so from our side, just supporting this launch campaign for the last 8 weeks, we've had, I think, a maximum, probably about 30 of our people out here. Working probably a core team of about 20 who've stayed with it throughout the entire 8 weeks. And the same is true when we were over in Munich earlier this year in the test campaign. We have a core of about 20 people who basically live with the spacecraft while she's away, and then numerous people dropping in and out for various different phases. So in terms of just the test campaign and the launch campaign, we've supplied quite a few people, but back in the UK, in terms of the number of people who have worked on it over the years since it's been in build in Stevenage in our site, I would estimate that at least 200 to 200 people maybe from across our company have at some point had some kind of interaction and input into this project.
Okay, and I can just finish off by talking about the science side. I'm just moving away from the window so we don't get too much light. In total, I would say in terms of the development of the data analysis software and in the science side of the mission, we've probably had about 70 people come through. And out of that, we have a core team of about 40 people who will be present, not continuously, but we'll have a very core team at the European Space Operations Centre, ESOC, during the mission to analyse the data. only from the science side. We then have an additional maybe 30 people coming from both from the engineering part who will actually run the operations for us at both ESOC and ESAC, which is the science ground segment side. So I think that the answer is many, many people have worked on this mission to get us where we are today.
Okay, so thanks. I think that that was a good question, because that gives sort of a perspective on the size of the endeavor, and you can imagine for the future LISA mission that the numbers would be even much larger. We have a few questions about once we are on at the L1 point. This is a question from Barbara, who is asking, how long will it take you before you have an idea that everything is working fine, as expected?
Okay, sound back on. Okay. So when we actually get towards the science orbit and we enter science orbit, the first thing we do is we have to commission the hardware. So commission means we have to turn all the instruments on, and we have to ensure that they're working the way we expect them to work. And sometimes we may have to tweak things here and there just to make it work properly. So once we do the commissioning, the last part of that, before we hand over to the science team, is we transition between the control modes of the spacecraft. So as I said earlier, when we're operating, the spacecraft flies around the test mass such that it protects the test mass from all the external disturbances. So we have to ensure that the control system works and allows the spacecraft to stably fly around the test mass. And by the time we do that, that proves, I would say about 90%, proves that everything is working perfectly. If something is wrong by, let's say, a factor of 10, we will never be able to get to the point where we can control the spacecraft. So by the time we actually start doing science operations, we know, I would say, 9% that everything is great, and we know enough to move forward with the future mission for the Large Gravitational Wave Detector. During the science operations, what we want to do is improve things. We want to make things better and better and better. And that's what you call the commissioning and calibration phase of the LISA-like mission. So we want to get it to be its absolute perfect, in the perfect operation, such that we can get the most science out of the mission. But to prove that the system is working, we get that almost immediately.
And we have a question from Arthur about the future, precisely. Are any of the parts of LISAPathfinder, if it's a success, going to be integrated into the future ELISA mission?
So are there any parts which will be used in the future LISA mission? So the LISAPathfinder, the critical technology which we really want to test on LISAPathfinder, are the thing we know as the inertial sensor. So that's the gold platinum cube inside its housing with the spacecraft flying around it. That's the part. When we first proposed LISAPathfinder, because it was a demonstration mission, we relaxed the requirements. So we didn't have to do as well as LISA requires in order not to spend too much money in the testing phase of the mission. However, we designed and built the hardware for LISA, not for LISAPathfinder. From all the ground tests we've done so far, as Vicky said, there's a huge ground campaign goes on before you launch a mission. All our tests are showing that we're doing actually better than the requirements. So when we launch this mission, I believe we will actually demonstrate the full LISA requirements. So we could take the inertial sensor and plug it straight into LISA, and that's what we're doing the mission for, and that's what I think we'll see from this. We'll also have other parts of the instrument, like the optical bench, which is manufactured in a particular technique, something called silicate bonding or hydroxy-catalysis bonding. We won't take the optical bench as such and fly it in LISA, but all the techniques we've developed to build this optical bench will be the same technique we'll use for LISA. So maybe the hardware won't be an exact copy, however the techniques we've developed for Pathfinder will be used to build the LISA mission.
Okay, we have taken a lot of your time, so there is a final question. Okay, that we got on the Q&A session. Maybe Volker, you ask it.
Yes. So Joan was asking, and I have the same question: will any of you get any sleep between now and launch? And Paul, will you get any sleep for the next 4 or 5 months?
go round and see.
Well, okay, yes. From the range or the launcher viewpoint, we are finalizing operations today, and we'll sleep tonight. Tomorrow morning, we will not work if everything goes well, and so we can relax a little before we go and take place on our stations for the launch.
Sleep. That's the question, is about sleep. I can tell you something. There were a few sleepless nights over the last years. But I would say that over the last year, maybe 10 months, I was able to sleep very well. And now I sleep well. And if I don't sleep, it's because there are activities and so on. I have full confidence.
So for me, I suppose luckily in a way and unluckily in some, my role as the QA for the actual physical spacecraft is obviously kind of over at this point. So I get to sit back and just enjoy the show tomorrow, which is great. So I'll be there having a little bit of a kip in the afternoon to make sure I stay wide awake until the early hours of the following morning.
And for me, will I sleep tonight? I hope so, but I'm not too sure. I think we're all getting very excited here, so I think we'll have to get some sleep tonight because tomorrow's going to be a very long day. But like Caesar, I also get full confidence that having seen the way the teams have worked here, it's just been phenomenal, both from the project side and from the launcher side. So I don't believe anything is going to go wrong. We had the launch countdown rehearsal on Saturday, and I was only an observer, but I was shocked how relaxed everyone was. So if we're so relaxed tomorrow, then we'll all sleep very well. Maybe not tomorrow night, but tomorrow, Wednesday morning, we will all sleep.
Okay, so well, I would like to, on behalf of all our learners and everyone who is listening, I would like to thank you so much for taking your time. And those are even though you seem to be very relaxed, those are tense times, I'm sure. And so it's we appreciate very much that you took this time to explain to us, full hour to explain to us, and there are many listeners, what is going on at this point. So I think that's a rare view of what's going on the launch pad a few hours before launch. And so on behalf of everyone, I would like to thank you very much for this great hangout. Okay, and so let me conclude. Sleep well tonight. Okay.
Thank you, and I apologise for the mix-up at the beginning. We just had a slight technical fault here of my computer dying. So.
Okay.
If that's the only thing that breaks, we'll all be very happy. We're all trying to get the final.
Okay, the final picture.
Thank you.
Okay, guys.
Bye.
Thank you. Bye-bye.
Bye-bye.
Bye.
Thank you.